Welcome to Data Science 1, Probability. Sums of random variables. Items we need to remember. Oh man, there's a lot here. Sample space, random variables, independent random variables, expectation rules, variance rules, covariance rules. Well, most of it will be pretty easy here. So far, you've probably thought probability seems quite theoretical. There's lots of math, there's so many distributions, and you're not sure how all this connects to data, right? That's ultimately what we're going to be after is, how do I connect my data to this probability? And that's where we're going to try to start building a bridge to inference, and I'm going to give you a little teaser example here in a little bit. But if we just a little bit of effort more, we can come up with some really useful results that we can actually apply to help us make some sort of inference. All right, so we're going to use a large number of random variables here. And the reason we're going to do that is because we can think of each random variable as being the value of our experiment before we've ever conducted our experiment. Okay, what might the value of it be? Well, we might get, if we take a sample of 25, we're going to end up with 25 numbers. Not one number, 25. So each of those 25 numbers will be measured. And remember, a random variable assigns a measurement to an outcome. So we're going to have a large number of random variables. Here we're going to make some important assumptions. Number one, each of our random variables will be independent of each other, meaning the outcome of one doesn't affect the probability of the outcome or not outcome of any of the others. We're going to assume it's identically distributed. So all the random variables come from the same sample space. And you can think of the sample space as the population, right? And all the random variables give the same probability distribution. So when we make our random variables and we're measuring things, if we're consistently measuring, for example, the number of successes before a failure, we're not going to halfway through it go, well, I'm too tired of doing that. Let's just measure the clock time until a failure. Right? We've changed the type of random variable there. We're not going to do that. We're going to keep everything identical. And this is called independent identically distributed, often denoted IID, and you'll see me use this. In order for inference, we must make sure that these assumptions are met, okay? Not that we should check this afterwards. Do this before you start, okay? A lot of people are like, let me check my assumptions afterwards. Well, it's too late. You've already collected the data. You've already spent the money. Don't do that. Design your experiment so that the assumptions are met, okay? All right, so we're going to have some notation here. We're going to say x1, x2, ... xn are n random variables from the sample space S to the real line. So xi is a function that goes from S to R. They're all going to be independent and identically distributed. So since they are all IID, we know they're going to have the same mean for each one of them. We know they're going to have the same variance for each of one of them. And since they all have the same mean and variance, we don't have to keep track of the parameters for each of one of them independently, okay? And since they're independent, we know that the covariance of xi with xj is equal to 0 when I is not equal to j. Now, we didn't actually prove that, but it is true. With little effort on your part, you can show that that is actually true. All right, so let's look at the sample mean, right? When you get a sample, what are you probably going to do with it? Most people take the average. So the sample mean is given by x bar, 1 over n, the sum of the xi. Now, this is going to be the theoretical sample mean. We don't have data yet, but we're saying what might the sample mean be, right? Just like when we did our experiments before, we said, what might the measurement be? Well, x bar is a measurement of the sample mean. What might it be? And can we find its expected value? Well, sure enough, we can do this. Because we built up all of this sort of machinery, we can find out what the mean is of this thing. So we can find the expected value of x bar. We know that this is the formula for x bar. We know that constants pull out. So there's the 1 over n. We pulled that out. We know that the expectation goes across addition, right? So we just push it across addition. We know that they all have a common mean, so I can substitute that in, and that the sum of the common mean, n times, is just n times that common mean, and we end up with mu of x. So this means that the expected value of x bar, our x bar here, our sample mean, is going to be the mean of our population. Okay, so this is, on average, the sample mean is the population mean. Now, there's some issues later that we'll run across that the population mean and X bar are actually never actually equal to each other, but on average they are. That means that we have an estimator for our population mean. This is huge. If we need to estimate the population mean, this is saying we can use the sample mean. Okay, this is a big result. Why do people just automatically take the average and they say, well, I guess it's a good guess at it? This is the reason why it's a good guess, okay? And that's what I'm trying to get across here. This is really important, and this gives us our justifications for doing a lot of the things that we do. Now, if you're a statistician, you're going to say, oh, wait, we would say X bar is also unbiased, right? I'm not really going to focus on that. I'm just going to point it out here. If you know what unbiasedness is and you study that, that's fine. Right now, we're just doing a cursory cover of that. All right, what about the variance of X bar? Well, let's give it a go. Do the same thing as before, right? We have our variance rules. We know that constants, when they come out, get squared. So I get 1 over n squared here. We know across independent random variables, right? We're independent, IID. Independent random variables, we can go across that addition. We know that it has a common variance across all of them. So we get n times the common variance over n squared, or sigma squared over n. Okay? So it's not just sigma squared. We end up with sigma squared over n. And this n in the denominator is going to save us. This is an amazing result, because if it was just sigma squared x, we would not be able to do nearly as much as we can with that n there. Okay, so what does this mean? This means that on average, we're near the sample mean. That's what the expected value x bar equals mu means. And it means this variance of x bar tells us how much we vary from that population mean. Okay? Because it's a variance of x bar. How much is x bar varying from sample to sample? Notice that the variance has n in the denominator. Here we have sigma squared over n, which means as n grows large, the variance goes to 0. So we have basically, as n grows large, we vary less and less from the mean. And this would kind of make sense if you think about it. The more information you have, the less variability you should have. Because variance is a measure of uncertainty. You think more information, less uncertainty, and less variability. All right, so let's look at an example here real quick. We're going to use the Bernoulli example because we haven't stared at it in a while. So here we know that the expected value of x bar is going to be the same as the expected value of any experiment, which is just going to be p, our probability of success. The variance of x bar is going to be the variance of each individual x over n, okay, which is p times 1 minus p over n. Now, if you've done anything in statistics with either a confidence interval or a hypothesis test on a single proportion, you will see this formula floating around in it. So this is where it comes from, by the way. It's not random that it showed up there. This is where it came from. So suppose n is equal to 25 and p is equal to 0.35, then we would expect p to be 0.35 and the variance to be 0.0091. if we had an n of 25. What happens if we had an n of 200? Well, the expected value is the same, but the variance has shrunk dramatically. Okay, it becomes 0.00001. So it's changed dramatically, and that's what we're going to try to make sure that we understand. Okay, so I'm going to do my little inference teaser now. I told you I was going to do. And I know this video is running long, but you can't put all this stuff together. There's got to be a reason for it, and here it is. Let's suppose we're interested in the failure of a USB stick drive, okay? Maybe we think that for a particular brand, the failure is about 8%. This would mean that Xi are Bernoulli, right? Each one is either going to fail or it's not, and once it's failed, it's done, right? You can't reuse it. And we're going to assume that they're all independent from each other and identically distributed. So if we took 125 of these USB sticks and tested them, we would expect, if it's true that the probability of failure is 0.08, that we would expect p to be 0.08. Now, it's not actually going to be that because we got to collect data and it's random, but this is where we would expect the mean of this thing to be. And if we go through, this is what we would expect the variance to be, which is 0.0005888. And if you take square root of that, that's 0.024. Now we're going to slam one of the rules that we know that we're kind of loosely putting together here just to get you moving along. There's the 68, 95, 99 rule that says most of the values of the sample mean should be between plus or minus 2 standard deviations, if you remember that, or between 0.032 and 0.128. Okay? This is what we would expect if we took a sample of 125, and if the failure rate is 0.8, we would expect this interval to capture this. So suppose we took a sample of 125 USB sticks. We're doing the experiment we said we were going to do, okay, and we found that 15% failed. Seeing that 15% failed would imply that our data is very rare because it's falling outside of what we would consider reasonable values for it, or the assumption of 0.08 is wrong. And this is where we're going to pick up with inference, is which is right. And we'll talk about that later. All right. So IID, independent, identically distributed. We can estimate the mean parameter because we know that the expected value of x bar is equal to mu. So the average, not too bad to use. We can measure the variability around it. With also this formula for the variability says the more data I get, the less variability about the mean I have, which means I have less uncertainty, which makes sense. This gives us a link to inference, which I just showed. Now we're going to formalize that in the next video where we talk about the central limit theorem. So see you there.